All right, so flow charting, very important part of algorithms. We talked last lesson is where we actually left off with flow charting as one of the points or one of the ways of doing algorithms or representing algorithms, where an algorithm is going to be some kind of step-by-step, okay, approach to defining a problem and applying the solution so that it can be solved on a computer. So it's not the only algorithm, as you'll see in our notes here as we go. So here's some examples of as it says, computational thinking, and some things that we would do that would lead us to an algorithm. So we start with a problem and we end here at the bottom with some kind of an algorithm. So some of the things that we do, we're given a problem, which is to design the Qatar logo for 2022 or something like that, so that it could be implemented in Lego. And so if you're going to do that, first, you might start with decomposition. Decomposition, remember, means to break the problem into smaller parts, then attack each of those parts separately, and then basically put the solution back together. Pattern recognition, where we would see that something can be repeated. That's pretty obvious with the tool that we're going to be using here to create this logo, which is a Lego block. You'd see a repeating there. You know, these things go together like that, and those things go together like that. There's some repetition there. Abstraction. The problem there is we might have these ideas in our heads. Supposing we say, oh, well, we want our logo to include a falcon. Well, a falcon's quite a complex animal, right? And you know, if you look at it close enough, there's a lot of detail in the feathers, the eyes, the talons, etc. So you would want to abstract from that and just reduce down to the minimum that you would require to sort of recognize it as the symbol that you want, maybe this falcon. So that's what we mean by abstraction. Removing, so perhaps feathers would not be necessary. Perhaps you just need a beak and some eyes, something like that would be enough. Then lastly, the Lego team would consider the application of that in Lego. You know, so how are we going to do that with, you know, maybe we need some little round Legos for eyes or something like that, and different colored Legos to represent a beak and other feathers, etc. And then we'd have an algorithm and how we'd put that together. So you'd have to have a bottom and a top, I suppose, and put them together piece by piece. Sorry, I'm not really good at building Lego. You could probably come up with a better way of explaining it, but that's my attempt at it. These points here are about the fact that when we have an algorithm, we have more than one way of expressing it. And these are three ways that we have of expressing it. Today, we're going to focus on flowchart, but we have these others which I've mentioned before also. Plain English, we can just say in short sentences what we're going to do. Now, what's necessary for that to be an algorithm, it has to have a start and an end, right? But in between that start and end, we can just say what we're going to do. That would be plain English. Something similar to plain English is pseudocode. In fact, when I first learned about pseudocode, the other thing that we used to call it was structured English. Pseudocode, structured English. So it's kind of like plain English, right? Except it's structured. That means besides having a begin and an end, we have some special words that we use, like we have while, this, do, repeat, until, you know, if, this, then. Basically, sounds a bit like computer programming. Third generation languages, kind of structured English, could be very easily translated into, when I first started programming, we would translate it into Pascal or Fortran or BASIC or something like that. And so it sounded a bit like them. If, this, then, that type of thing. Which, by the way, that kind of structure carries over to our modern programming languages. C, not so modern. It's kind of old, but it does that if stuff and it has case, etc. But Java, Python, and they're different, of course, because they have object, object oriented. Okay, so here's some other examples of algorithms which you may be familiar with. You may have even used these algorithms, and they're not necessarily on a computer. You could put these on a computer, but they're not necessary. So, for example, anybody can pick up and go to a website and convert Celsius to Fahrenheit. You could probably, a lot of you here could do that maybe in your head, or at least on a calculator, because you're familiar with the algorithm that's required, right? So if you have a Celsius temperature, you're going to add 5/9 of it, or multiply it by 5, divide by 9, then add 32 to it or something like that, and then you're going to get your Fahrenheit. And you do the opposite to go back. So it's a fairly simple algorithm. And if you listen to what I was saying while I was talking about that, you realize it's kind of like a mathematical, almost an equation, right? This is equal to this with some little conversion, mathematics with multiplication and addition and division. Computing an average grade also. You could represent this in some kind of mathematical thing, like we take the sum of all the values and divide it by the count of all the values. And that gives us our average. Very, very common thing in computers, and you'll have to do this. Sorting and finding something. Now sorting and finding, there's more than one way to skin a cat, they say, right? Okay, so if you could Google on these and you could find, I don't know, 4 or 5 different algorithms for sorting and for finding. And I mean, the simplest way, say you have a list of things, the simplest way to find something simple, what I mean by simple is without you doing any thinking, is a serial search. You just start at the start and go to the end and see if you find it, right? That's a serial search. That's the simplest. A much more efficient way would be a binary search, which is you take the thing, okay, first you sort it. So how do we sort things? Well, what we do is we look at this one and we look at the one beside it. Is it bigger than the one beside it? No, okay, well, we swap places. This kind of thing is called a bubble sort. And you can go through a whole list and swap everything. It's not really a hard one. You can find that algorithm, but once you've sorted a list of things, you can find the one that you want in a sorted list by using a binary search, where you look at the thing, look at the number. Is it bigger or smaller? If it's bigger, you go to this half. If it's smaller, you go to that half. And each time you reduce the size by a half. And eventually you must get there, depending on what number you pick. You'll get there fast. We talked about that number in a list. Greatest common divisor of integers. This Euclid, Greek as far as I know. But I mean, so we're talking about more than 2,000 years ago. And so I don't think he had a computer, but he was able to develop an algorithm, right? It's really kind of like almost mathematics, but it's a repetitive thing, right? So if we want to find the greatest common denominator of 2 numbers, we divide one number by the next. We find the remainder. Okay, if the remainder is 0, then the number that we divided by is the lowest common denominator. If it's not, then we take that number and divide it by the remainder. And we keep doing that until we get 0. So Euclid's algorithm, it's not very complicated. It's been around for a long time. That is an algorithm. You don't have to have a computer to have an algorithm. All right, I'm kind of talking kind of fast. Am I talking too fast? We okay? Yeah, that's good. I like to talk fast because then I can finish quicker. It's okay with you guys, all right? All right, that's good. Okay. Also because it's also boring listening to some old guys standing up before they're talking. So you've seen a flow chart. The next couple of slides, I'm going to show you some of the components of the flow chart. And so you should be familiar with them, right? So we need to know what are the parts of the flow chart. We need to know how to make a flow chart. So as it says there, it represents the processes of an algorithm, can be represented in a flow chart. It has a start and an end. We have symbols that represent the different things that we would do. We have in algorithms this concept of, oh, well, let's look at it. I'll get to that later because this one's here, right? So here is a flow chart. This represents an algorithm. This is a nice algorithm because it has a decision in it. Decision, do you see the diamond? The diamond is a decision. What's important in the decision is that you branch. That is, you will complete one set of code if this is true, which is yes. If it's not true, you will complete a different set of code. And this is very important in computing. That allows us to do so much, right? I mean, that's your zeros and your ones there. You can think of your no as your zero and your yes as your one. And that's how computers work, right? Zeros and ones. So when it gets to a decision, depending on the data that we've got now, let's look at these nice symbols. This sort of rhombus shaped symbol that represents some input or output. Okay, in this case, it must be input. So we checked some input, then we tested it. So we got a decision. Based on that decision, if this time was before 7, then we take the subway. There's a process. Process got a rectangular shape, and that will reach school. If it's not, then we take a taxi, which will cost more, and we reach school and just paid more money. So there's a flowchart. Think you could do it for a process? Well, let's see what else we got here. Okay, so here's some of the symbols that are represented in a flowchart. If it's got rounded edges, so that's a connector. Could be a start or a stop, or it could be go to the next page if you got a really big flowchart. Some, a flowchart that you can't see on one screen or can't fit on one page of paper. Then you're going to have connectors. So you can use that, go to the next page or start or stop. Every flowchart must have a start and a stop. Process, we're doing something. We've got our inputs or our outputs. Kind of looks like a process, but it's really the data that's going to be used by the process. Okay, and then the decision, it's either going to be yes or no. The arrow is important. We have to follow the arrow in the direction that it's pointing. That's the way the process works. So starting from the start, the arrow will be coming out of the start and going probably to a process, but maybe to one of these things. And then from there, it continues. All right, so here's one. Idris app. Do you get to come into the college today? Okay, so you show up at the front gate. The guy at the front gate asks you to get some input. Show me your screen. That's input for him, right? Because when he looks at it, that becomes input. Even though it's not printed on anything, he can see on your screen. That's output from your little computer, but it's input for him. This process is not happening on your computer. This process is happening with the security guard, right? This is what you're doing. You say, okay, you got green on your address, so I'm gonna let you in. You got red. Sorry. Go home, or go straight to primary health care and get a PCR test or something. Whatever. Okay, so we got some. These are all just. These are all just. How do you say? Extensions or alternates, representations of the same thing. Right, so we got our decision boxes there. We've got our input output things. That almost looks like, okay, so that's putting something on a screen, do you? And then the decision is here. Yeah, all right. Would you like to share a meal? So we put the, okay, it's kind of fuzzy. We got a process with things like, now I was supposed to show you a video here. If you look at the slides, if you download the slides, there's a video there from what is it, the Rock from the Sun or something like that. I don't know, the Big Bang Theory. You guys watch that stuff? Anyway, so you got a guy there who's sort of socially awkward, and but he's really, really smart, right? All those Big Bang people are really, really smart, but socially awkward, doesn't really have many friends. And so he wants to make some friends. So he calls some people up, right? And he'll do anything. You can tell by this flowchart that he'll do anything to have a friend. Any friend is good enough. All right, if they're willing, then they're my friend. Basically like that. So he calls them up. If they're home, then he asks them, would you like to have a meal? And they say, yeah. Then we're going to dine together. Then we become friends. Maybe they're not home. Then he's going to leave a message. And then he's going to call them back, right? If they call him back, then he's going to ask them, you want to have a meal? And they're going to become friends, right? Okay, so they're not home and they don't call back. Then we're going to ask them, all right, hold on. No, he's going to call them back. Then he's going to ask them, do you want to have a meal? And they're going to say no. This could also happen when they answer the phone. Anytime they answer the phone, if they say, no, I don't really want to have a meal, then he's going to ask, would you like to have a coffee? Oh, no, he doesn't ask. Would you like it? Because down here, we're going to have, yeah, you're going to have a coffee. And if they say yes, then they get to be friends. If they say no, then would you like to, I don't know, what does he do? What does Big Bang people do for fun? They want to play video games. I don't know. Maybe he sits around and writes physics theories or something like that. Freaks my mind. Would you like to do that fun stuff? And yeah, I like that fun stuff. Okay, great. Now we're going to be friends. But it's quite possible that they will end up at that other end, which would be not a friend, I suppose. This one here, we can keep. He's going to see the n equals 3. That means, oh, or are you interested in computer games? No. Oh, well, he's got 3 interests, obviously. So are you interested in, what else is he? Does he do horse riding or anything like that? Are you interested in bicycling? Yeah, okay. When we get to the third one, then it's no, then it's wrong. But could be one of those. What's good about this is it shows a common thing in a computer thing. It's almost like a menu. It's if, then, else. If, then, else. If the guy is home, then I ask him if he wants to have a meal. Else, I wait for a call back. Yeah, it's like that, right? And then there's another if, then, else. There's another. You'll come across that a lot in your programming. If, then, else. Very nice. Very, very simple flow chart here. Are we still going okay? Because I'm going fast, but it's still taking long, isn't it? Simple flow chart. This flow chart doesn't have any branching in it. It's got a lot of inputs, 3 inputs, then a process, then an output. Oh, seems okay. So basically what this process is, or this algorithm is for, is calculating the grade based on the fact that you have 3 grades and we get the average of those 3 grades. 3 grades come from assignment, quiz, and test. What if you mix it up a bit and you say, well, we want to be a bit more specific about that. The assignments were 20%, quiz were 30%, and the tests were 50%. So we're just going to multiply them by the percentage. And you know, the percentage is going to be 0.2, 0.3, and 0.5. So we take the first grade, multiply it by 0.2, the second by 0.3, next one by 0.5, add them together, and that's your overall grade. Okay, so I don't know if this is familiar to you. You've been in college or school for a long time, and so you probably had a lot of this happen to you, right? I sure had a lot of this that I had to do. So hopefully it's something that's familiar to you. Okay, so what you're supposed to do is draw a flow chart for making tea. What do you reckon? You guys up for it? I don't think green is a good color for flow chart. I'll do it here. Okay, so we're going to start with a start. And I'll put a round around it. Okay, so making tea, that's the first thing that you're going to do. And think about it, is there any decisions or anything? I'll give you some hints about decisions. Some people like to have lemon. Some people like to have sugar. Some people like to have honey. Some people like to have milk. Some people like cream. You know, some people like Earl Grey tea. Some people like Lipton. You know what I mean? There's lots of choices. All right, so, okay, where would you start? Get a cup. Okay, so we start with an arrow, get cup. That's got to happen to everybody. Okay, so that is not information, and it's just a process. Then, straight away? Okay, so there would be a controversy on this, because some people add milk first and some people don't, right? So are you going to have any choice in that? What if you don't want milk? Oh, everybody wants milk. Oh, okay, yeah, all right. So this is at your house. You add milk to the cup. Is that the correct way? See, I told you there's a controversy. Somebody else is going to say add the milk last. Okay, then. Oh, sorry. So I put it as a question. So what if I said no? Then what? That's what, we got a controversy. Some people said no, so I'm making a question. All right, so we'll go on. What's the next thing after adding milk? All right, is that how you do it? You put tea leaves? Okay. Okay. You add sugar after the milk? Do they get to have a choice on that? All right, okay. So I'm going to give them a choice on that too. All right, what if they said, no, we don't want milk? Then, sorry? All right, so you have to have water, but you can't put it before the milk, right? Am I right? So does the tea go in before the milk? I mean, before the water? So, you know what I mean? The tea has to go in. You put the tea in with the milk? Okay, so.
You take water first, and then you add sugar, and then you boil it for some time.
Okay, well, isn't that up here? Before adding milk?
So maybe take.
I don't know. Anyways, if it was me, I would have boiled the water first, but but that could be a side thing. Would that be all right if we did that? All right, so all right, so get the cup, and I have to come back to this. Can I and boil the water? No, it's a separate process because if I put it in there, it's like we boil the water in the cup. You don't do that, do you? No. Don't you boil it in something separate? Yeah, so can I put it up here before the cup? So we got water boiling. We get the cup. The water's not going in. That arrow does not mean that the water is going in the cup. It just means that we boiled the water before we got the cup. We'll say something different for when we put the water in the cup. Okay? All right. So you guys right with that? Okay, so we boil the water, we get the cup, we add the milk. What if we didn't add milk? I think that you could actually take this arrow and put it home. Yeah, then we'd have two arrows coming in. Could be, it's kind of weird. Both, whether or not you add the milk, we then ask the choice, do they want to have the sugar? So the sugar is independent of the milk. Oh, it's okay. Yeah, we can do that. No, we're still going to see. So do we add sugar? Then what? So let's say we did. Yeah, I'm running out of room, so I'm going to go this way. After we added the sugar, what if we didn't add sugar? I think that those arrows can both go to the same place, actually. It's just that maybe we added sugar and maybe we didn't. Somebody's going to tell me I've done this wrong, but anyways. What's next after we put our milk and our sugar? Then we tea? Where? Put the tea in the cup, or you put the tea in the kettle? Sorry? Okay. So this is a choice here. It's kind of a messy one, but this is a choice. It's basically choose milk or sugar or both. And so what we could do is that what we were saying. If add milk, then go and add then this. Else, we still go to the same place, right? So what we're giving ourselves a choice. It's otherwise, yeah. Anyway, so we're going to put we're going to boil the water. When we going to add the tea? No? Okay, so do we add the tea to the boiled water? Add tea. That's going to happen every time. And the next thing is going to happen every time too, right? Which is going to be to pour the tea. Right? And then we got a cup of tea, I guess. Was that enough? I think it's probably not the best one, but you get the idea. It's something that we could do. It is a process. It kind of would work. We could kind of make a robot do it. Okay, so just some points there that came from the previous lesson. When we do algorithms, they should be something that can go into a computer. These things are necessary for it to go into a computer. Instructions, programming constructs, input, output should also be correct. And it should be efficient. Repetition is part of a programming construct. We use another word for it. We also call it iteration. This is what computers are really good at. This is where we first used computers in banks and things like that to calculate people's amount of money in their accounts with the transactions that they had every day. Those are kind of the first things that were being used by computers. The naughty student who had to write out something about what they did wrong, that they might, while they're doing that 100 times, the idea of the 100 times punishment was to make them think about it so they wouldn't do it again. But if they were a computer nerd, they might be thinking, well, you know what? I'm repeating this process over and over 100 times. Maybe I could get a program where I could just write 3 lines of code and the whole thing would happen 100 times without me having to do it. So if they had a little computer, maybe they could type in, repeat 100 times, I will not do this. With 3 lines of code. That if they were a computer nerd, they might be thinking like that. And yeah. So if they were, they would be thinking in terms of repetition, which, as you see here by this fellow here, is kind of a smart guy from like the 1960s. He sort of said, well, this is what we do with computing in the 1960s. And it's something that we still do. Our computer programs have sequence. That just means that one thing happens before another thing. And we can tell which is going to happen first by where it is in the program. Stuff at the start of the program happens before the stuff after. Repetition means that we can do the same thing. We can go back, we can branch. We can go back in our code, and that's why I got arrows going all over the place. We can go back in our code and do something again without having to sort of write it out again as a bit of code. We can just go back to it and branch back to it. And selection is branching. Selection means that we can do an if, then else. That's selection, if, else. So repetition allows us to save ourselves a lot of time when we're calculating the balance of people's bank accounts at the end of the year. Also, governments were some of the first users of big computers. Governments still big users of computers. They are doing things like IRS, right? But in some places they collect income taxes, and so they keep records on everybody's finances, and yeah, get information from the banks, things like that. And so there's a lot of repetition. Oh, other ones. When I was talking about governments, governments provide for services like electricity and water, but it's not free, is it? So they were some of the first users of computers. They had to calculate how much electricity was being used by every house, every day, all the time. And at the end of the month, they had to write a report for each one that computed how much electricity and how much they had to pay. That was some of the first use of computers. All right. So they had their nice big computers when the rest of us were just, using calculators or adding up things on a slide rule. They were using computers to print out your water bill long time ago. And it was the point that I was supposed to be making here, I think, is that was very repetitive. My water bill was calculated the same as your water bill, right? The only difference was, what the measure was, the input data, but the actual process was the same for everybody. So you could repeat that, repeat it and repeat it and repeat it, right? For every customer. Load customers, run water bill cycle. Out comes all the bills, right? Very repetitive. And okay, so we got an example. Yeah, the school punishment. I'm sorry about this one. I will not. Yeah. Instead, what I will do is I will write a 3-line code which says repeat until 100. I will not. Yeah. Okay. So you wouldn't do this, would you? You wouldn't write all that. Well, if all you had was a piece of chalk. But if you had a computer, you would definitely write a little program. And your program would look kind of like this in an algorithm, which would say, okay, well, what I have to do is I have to write this little statement. but I'm going to do that 100 times. So I'm just going to put that in a loop, and I'm going to keep doing it until I've got 100 times, or 10 times, or whatever. And that is our sort of our basic loop. Oh, and all right, something like that. Well, we're almost finished. This is the last little activity. Right, so you need to write a little program or an algorithm which asks the person their age and then prints happy birthday the number of times that is their age. What do you reckon? This one's easier than that one. Because the problem with that one is we couldn't all agree, right? I mean, I started writing things up there that were different because milk in the cup. It's obvious that I don't drink tea. Okay. But that's the problem. I mean, maybe we should have learned from the milk and from the tea one is before you actually go and write your algorithm, you should agree. You should talk about it and agree, and then you'll come up with something that makes a bit more sense. But I think this one is pretty simple. What we're going to do is we're going to get the person's age, right? So that's going to be input. And we're just going to ask them, what's your age? And then what we're going to do is we're going to, oh, well, what would you do? How would you do it? First, we get their age. At the end, we somewhere in the middle here, we print happy birthday. So that's another output. So we've got an input, which is their age, but this happens a number of times. So so we know there's going to be a loop in there. Okay, so now we need to fill in that, right? They're going to print happy birthday the number of times that is their age. So this number is going to come out there. And yeah, what? The age is here. Why? You're on the right idea, iterating. That is, if you started with the 0. Okay, so you would start, you've got a counter, right? I think what you're saying is you have a counter. So can I set a counter to 0? So I'm going to set a counter to 0. And what we'll do then is we'll have, we'll move this so I got enough room. And I'm going to have a decision here. And it's going to say, I'm going to compare the counter to the age. And then down here, I'm going to increment the counter. So that's where I put your add, okay? Counter plus 1. So what would be the decision in here? Okay. So counter equals 0. I got to make sure I got that in the right place. But oh, you know what we're missing is the happy birthday. Then I have to print happy birthday. Now we're missing another thing as well. No, that's it. So before we print happy birthday, we're going to compare these. And what will we decide? How will we decide whether we will print happy birthday or not? We would say, is the count less than the age? Because we're going to add the counter 0 after we print happy birthday. We're going to add to the counter equal count plus 1. So here we could say, is count less than age? If it is, then we print happy birthday. Right?
So can we use the if statement?
Sorry?
The if statement.
Yeah, this is an if statement. This is an if statement. This is an if statement. Whenever you see a decision, it's kind of like an if statement. So if the count is not less than the age, then the count is equal to the age, or it's bigger than the age, in which case we end. All right, so we can end. If the age is 0, then we don't say happy birthday, right? If the age is 1, the count is 0, we say count is less than 1. We print happy birthday, we add 1 to the count, and we go back here and go back into the thing. This would be the algorithm, I think. Okay, so let's test it with a couple of numbers. Okay, so somebody comes in and their age is 5. Okay, get the age, 5. Get the counter. So we got our age and our counter. Put age here, counter here. Age is 5, counter 0. Is counter bigger than the age? No, so that means we go here. So we're going to print happy birthday once. Okay, now counter is equal to 1, right? Because we added 1 to it. Then we go here. Is count less than the age? Count is 1, age is 5. So count is still less than the age, so we print happy birthday again. So we're doing happy birthday twice. Now age is 2. Get it? Age is 2. Is count less than age? Yes. So we print happy birthday again, right? And we go down here and we add 1 to the count, 3. Is 3 less than 5? Yes. So we print happy birthday again. And we add 1 to the count is 4. Is 4 less than 5? Yes. So we print happy birthday again. We add 1 to the count. Is 5 less than 5? No. So we end. How many times do we print happy birthday? 5. So it works. You with me? That's how you would do that algorithm. Anyways. Class? That's it. So what do we got? That's all on this lesson. I'm going to stop the recording.